Am I audible, sir?
Okay, so maybe I can get started. Would it be possible to share a link to the YouTube screen in the chat so that I can also share it with the students, and I think I can also keep track of any questions from there. I think I'm meeting some of you who have joined for the first time, and welcome back to those who have been around before. So I'm going to share my screen, and could you please give me a +1 in the chat if you can see my screen?
So that if
Oh, okay. 1 second. I just want to confirm if this is the correct Zoom link, right? Because the YouTube title says PDSA. So that is a data science course, right?
Kindly check the chat box.
Okay, I'm sorry. Did I end up joining the wrong Zoom meeting? Oh, okay.
Everyone was asking about week 5 question. Okay.
Okay, this is correct. Fine. So all of you who are attending, you're here for competitive programming. Yes, I hope there is no confusion. Okay. Perfect. All right. Thanks, Sudhanshu. Take care. So let me just get started here. So the first thing I wanted to talk about was the solution to the programming assignment from week 9. So let me just recall what the question was, and we'll take it from there. So what we were given was an array of numbers. I think it was one indexed. I would just denote these numbers as A1, A2, and so on through AM. And what we were allowed to do was the following. So we were given, so we had n numbers and we had n good pairs. And each of these good pairs was essentially a pair of indices, ij, with these indices ranging between 1 and n. And what was the additional property of these good pairs? Does anybody remember? Could it just be any random collection of pairs, or was there some constraint?
Addition of I and j should be odd.
Exactly. So I plus j is odd. That was a property of the good pairs, which I think one thing that Surya Prakash had mentioned in the previous live stream was that what this implies is that either I is even and j is odd, or I is odd and j is even. It cannot be that they're both odd, because if you add two odd numbers, then you'll end up getting an even number. And of course, if you add two even numbers, you continue to get an even number. So that cannot be the case. So any good pair involves a combination of an odd number and an even number. So they have opposite parities. Okay, so that is one thing to keep in mind. We'll see how it ends up being useful. Now the question was, how many operations of the following kind can you perform? So what can you do with a good pair? You can take AI and AJ, and you can find a number which divides both AI and AJ, and you can update AI to AI divided by that number. I think we used V to denote this, and you can take AJ and update it to AJ divided by B. So if V is a common divisor, then in one update, we can do the following to the two numbers which are involved in a good pair. And you can, let's do maybe a very simple example where let's say the numbers are something like 150. Okay, so n is equal to 2, and this is all that there is to it. I want to emphasize that you can perform this operation multiple times for the same pair. It doesn't have to be that one pair is only involved in one operation. So one thing that I could do here at this point is I could say that, 150, 50 divides both 150. So I can apply this operation once to come down to 50 and 1. What happens after this though? I think, let me just recall that I think you are only allowed to work with, you're only allowed to do this. So division by 1, we want to disallow because otherwise you'll keep going forever, right? Because 1 divides into everything. So at this point, let me just confirm that the language of the problem statement. Yeah, so take one of the good pairs ik, jk, and some integer v strictly greater than 1. So as you can see at this point, we will essentially get stuck because there's nothing bigger than 1 that divides into both 50 and 1. But for this example, is this the optimal answer? Consider that you want to know what is the maximum number of operations that you can perform of this kind. And as I said, you're allowed to use the same pair for multiple operations. So given that, can somebody tell me if this is the best thing to do to divide both numbers by 50? Is there something else that you can do which will give you a larger number of operations?
2525, ma'am.
Exactly, 2525.
Not 25 and 5.
2, 5, and 5, right? Okay. So, right. So you can drag this out a little more by using smaller divisors. So instead of directly dividing by 50, it's a valid operation, but it does not let you, stretch the game. So think maybe Bollywood and not Hollywood and try to see for how long you can drag this out. So for instance, if you use 25 directly, again, that would be like, it will take you to 4 and 2, and then you can use 2, and that will be 2 and 1. But instead, I think what you were saying is let's go with 2 first. So that will bring it down to 50 and 25. Then you can use 5, which will bring it down to 10 and 5. And then you can use 5 again, which will bring it down to 2 and 1. Yeah. So, right. So this allows you to go from, so the first thing that I did was just one operation, then we did 2 operations, and now we're able to get to 3. And I guess you cannot do better than 3. Can you do better than 3? So let's look at the prime factorization of 50. So 50 is 5 times 5 times 2, right? So that's, that's pretty much all the factors that are available, the atomic factors. So you cannot push it to more than 3 operations. Hopefully that is kind of clear. Yes. So, okay, can you give me a +1 in the chat if the problem description is okay, or like what we need to do? Hopefully that is clear. Okay, great. Yeah, thanks so much. So what we want to do is figure out like for how long can we draw this out. So in fact, let's just continue thinking about what would the answer be if it was just 2 numbers involved. So if it was just A and B, then I don't even I know that I just have to keep applying this operation as many times as I can between this one given pair. So what is a systematic way of figuring out this maximum for just these 2 numbers? Anybody? Okay, so the GCD is what we did last time, right? We said 150. GCD is what? The greatest common divisor is 50. but then you are finishing off the problem in one shot, correct? So the prime factors of the GCD, exactly. If you look at the prime factors of the GCD, that'll help you drag it out. So basically you write A in terms of its prime factors. So let's say it's P1 to A1. Let me just write it with repetition. So P1, let's say P1, P2, P3 are the prime factors of A. And these need not be distinct. And let's say the prime factors of B are like Q1, Q2, and so on, up to some QR. Here also maybe up to some PS. Okay. So essentially, I want to know what is the largest number of common things that I can find out here. Okay. So whatever I can find, if I can basically match them off, essentially, this is already feeling like some sort of a matching problem, right? So I want to find, so imagine making a vertex for every prime factor of A. Imagine making a vertex for every prime factor of B. And, I simply add an edge between two factors if they happen to be the same. So let's say these two are essentially the same and so on. Right. So essentially what I'm looking for here is some sort of a maximum matching. So whenever I find two prime factors that are the same for both the numbers, I can just pair them off and send them home. I can apply one operation. And notice that, you'll have to argue this a bit formally, but intuitively it should be clear that you really cannot do better than this, because these are really the atomic factors. You cannot divide by anything that is smaller than these numbers, because there's nothing that divides into these numbers. These numbers are prime, right? So, so there's some intuition for why there might be a graph involved and why this may correspond to something related to matching, which in turn we have seen is something that is related to flows. Okay. So let me try and see if I can build this out for the more general setting. So, and here is where I'll try to use the fact that the sum of the indices were odd. So on one side, let me sort of collect all the numbers corresponding to the odd indices. I'll just chill out and do it with maybe an array of size 10 or something. So notice that any good pair will involve numbers that go across, right? So you never have a good pair between two vertices on the same side, nor will you ever have a self loop, right? So any number plus itself will not really, an index I plus I is going to be 2 times I, and that will not be even. We are promised that the sum of good pairs. So even though the constraint says 1 less than or equal to ik, less than or equal to jk, less than or equal to n, this less than or equal to will never actually be equals, because ik plus jk is odd. So if ik was equal to jk, then this sum would be 2 times ik, and that is not odd. So they will never really be equal. So that should be, that should be clear. So there are no self loops in this graph, and every edge is basically going from one part to the other. I mean, I haven't really drawn the edges here, so maybe I should take that back. What I mean is any good pair will involve a vertex from one side and a vertex from the other side. Now what you could do is essentially for each vertex here, let's introduce its prime factors. I think this time let me just, you could do it either way. You could introduce a distinct vertex for every prime factor, or you could introduce a vertex for, every distinct prime factor, and then we can use capacities to determine, to encode basically how many prime factors there are. So actually, maybe let's again do this with a concrete example. I think the example that was there, one of the examples was 8, 8, 12, right? So let's see what happens if maybe, so this is one prime factor here, 2. and here you have 2 and you have 3, right? So this is actually your whole instance. Let me bring these guys center stage. So what I want to do is basically say that, okay, look, this prime factor and this prime factor are the same. So let's kind of relate them. But suppose, so here we know that this prime factor occurs with a multiplicity of 3, and here this prime factor occurs with a multiplicity of 2. So remember, 12 is 2 times 2 times 3. And these guys just 2 times 2 times 2, 2 times 2 times 2. So this edge, intuitively what will happen is that the flow that we pass through this edge will basically tell us the, the number of times we want to take the pair A2, A3 and apply the operation with V being equal to the prime factor that this vertex is representing. So this vertex here is representing the factor 2. And this edge, if there is a flow of 5 units, that means what the flow is telling us is, okay, take A2 and A3 and divide it by 2 5 times. Now, if you don't have 5 2s on one of these numbers, then we cannot do this, right? So we have to constrain the flow. So the capacity can be essentially, in this case, min of 3, 2. And similarly here, you could draw in an edge and again have a capacity which looks like in fact, depending on how you choose to construct the graph, some of these capacities will become kind of forced from some other edges that you draw. So for example, you could say that you have edges also from this group. So for every vertex, so in general, what's going to happen is you'll have a vertex and you will have other vertices corresponding to its prime factors. These are and you could have these capacities being, so if a prime factor P appears here, so let's say you have a prime factor P which appears B times, then the capacity of this edge can also be B. It's to say that that's the number of that's the number of times that P can even be used. And if there is some other number, let's say on this side, we call it C, and that's going to have its own set of prime factors. Right. So let's say this is some prime factor Q that appears okay, D times, then the capacity of this edge would be something like B. And if P is equal to Q, right, then we are going to add this edge between these two vertices. So this will happen when P is equal to Q. So notice that you will not be able to push a flow that is larger than min of B comma D, because if you try to push, let's say as was the case here, B is 2, B is 3, and D is 2. So if you try to push a flow of say even 3, that flow will go through here, but it will not be able to enter, this flow lands up at this vertex. And from this vertex, there's only one edge for the flow to get out. There is no other respite. But this edge is capped at 2. So you'll not really be able to push, higher flow. So this edge, even if it does not have an explicit capacity constraint, it won't matter. But if you want, the right thing to do would be to say min of B comma D is the capacity on this edge. Okay. So this is kind of how we will construct the flow network. So for every vertex, we will introduce a group of vertices corresponding to its distinct prime factors. and we'll add edges from the vertex to the prime factors with the capacities corresponding to the multiplicity of the prime factors. And between two vertices which belong to a good pair, so let's say this A is some, it's the number associated with some A of I, and this C is the number associated with some A of J. So if I comma J is given to be a good pair, then what we will do is we will look at these vertices and we'll connect those which have the same label, we'll connect those with an edge. And as I said, you could set that capacity to be the min of the capacities of the two multiplicities that are involved. Okay, so that's more or less your flow network. You'll need to add a S and a T to make the network complete. The natural thing to do is to add a source to all the numbers representing, say, the odd indices, and a target adjacent from the numbers that represent the even indices, or the other way around. It doesn't really matter which set you put on the left and which you put on the right. And just really try to compute a max flow. Again, I think these edges can either have infinite capacity or capacity. The capacity will automatically get capped at the sum of the powers. So it'll automatically get capped at the number of distinct prime factors of A1, of A3, and of A2, and so on. Okay, so so again, you could write down that capacity explicitly if you like, but it's kind of implied by the other capacities that we have thrown in here. If you don't want to worry about capacities, or more generally, whenever you put a capacity constraint, you want it to be unit capacity, you could introduce a different vertex even for copies and keep them all capacity 1. But this way, the number of vertices that you have kind of reduces. So I think this is more efficient to push the information into the capacity constraint instead of creating multiple vertices. So there's actually two ways that you can solve this. It turns out that the number of operations really corresponds to a matching between the set of green vertices that we have introduced here. As you know, you can find a matching by running a max flow pretty much in the way that in the flow network that I've described. So you could either run the max flow algorithm, it will automatically pull out a matching. And just in case you're familiar independently with bipartite matching algorithms, you could do that directly as well. So that's fine too, but that's not something we've looked at in the course. So I think the expected answer really is to run max flow instead. Okay, so so basically, why does this work? Let's say that you have a flow of some value. That flow is going to essentially, so between every pair of vertices that you have an edge in between, the flow tells you, this is the amount of flow that I'm running through this edge. What does that really mean? You look at which group this came from. If this came from AI on this side and AJ on that side, what this flow is telling you to do is it's saying, well, take AI and take AJ, and let's say the amount of flow that you were passing here was F. The instruction is that you can remove, so let's say this prime factor was P. So it's saying that you can remove P copies of F from both sides, but do it in F steps. So it will count as F operations, right? So draw it out, but you can perform F operations between the good pair AI and AJ. And notice that because of the capacity constraints, you will never be in a situation where you're performing an operation and you're trying to remove a prime factor which is not available, right? So, so every prime factor that you remove, so it's possible that if you go back to this example, for instance, both of these 8s have 3 copies of 2 sitting in them. But on the right-hand side, you have 12, and 12 can only accept, getting divided twice by 2, right? So, so even if the flow tries to push, let's say, so these capacities are what? I mean, these capacities will be 3, right? Because 8 has 3 copies of 2 in it. So if the flow tries to push, 3 units of flow on both of these edges, it's going to get badly stuck here. So the flow knows that on this edge, it can only push 2 units. So as a result, the flow will either get divided as, 1 and 1, or 2 and 0, or 0 and 2. it'll be one of these combinations. In any case, the total value of the flow will end up being 3. So either it will say take the first 8 and 12 and divide once by 2, and then take the next 8 and 12 and divide once by 2 again, or it will say take one of the 8s and 12s and divide by 4, essentially by dividing twice by 2. Okay, so depending on what flow you get, one of these solutions will essentially crop up. You can also check that if you come up with some solution, some sequence of operations that you can perform, then you can realize it as a flow, because you look at every step in your operation. It must correspond to either a prime factor, or if you're being suboptimal, it will correspond to a collection of prime factors. Like when we were removing 25 from 50 and 100, it can be broken down into 5 and 5. So you can look at between 50 and 100, you would have 5 and 5. So 50 would have, so let's say 50 is on this side and 100 is on this side. So 100 has how many copies of 5? So it's again 2, I think. So 25 into 4, right? And this is 25 into 2. So both of them have 2 copies of 5 in them. So the capacity of these edges is going to be 2. So if the operation says, remove 25 once, well, an optimal operation will never remove 25 once, because it can be broken down into removing 5 twice, right? So, sorry, I just noticed the comments coming in on YouTube. I don't know if you're still around, but Sandeep, yes, this is for the NPTEL course on competitive programming, and to, I guess, Vamsi Krishna and Mohammed Shakib, hello and good evening. So good to see you here if you're still around. All right, so just coming back here, notice that an optimal sequence of operations will never try to push out a composite number in one step, because then it's not optimal, right? You can break it down into 2 steps corresponding to prime factors, 2 or more steps. So once you do have an optimal operation, will essentially correspond to a flow. So every step, will correspond to 1 unit of flow, and overall, you can quite naturally translate a sequence of operations into a valid flow function on this network. Okay, so I could explain this a little more explicitly, but if the main ideas and intuition is clear, then we can move on to talking about other things like the DP assignments and so on. So let me know, especially for those of you who are tuned in live, did this make sense kind of, or do you want me to repeat any aspect of this? Okay, so I'll just wait for a minute or two for a signal in the chat. So you can let me know if you're comfortable if I move on. Okay, great. Thanks, Sudhanshu. So I would say this is the heart of the construction, and you can try to argue both ways in terms of, how a flow will correspond to a sequence of operations, where the length of the sequence is equal to the value of the flow, and correspondingly, any optimal sequence of operations will correspond quite naturally to a flow whose value is equal to the length of the sequence of operations. So that is something that I think I tried to show it in a slightly hand-wavy way, but I'm sure if you sit down for a few minutes, you'll be able to show it more formally. Okay, So, all right. So before moving on, Sunny, you're asking for some tips about how to clear the upcoming exam with good marks. Okay. So I will say that the format, okay, I think cheat answer is that we will be doing one last live session sometime in the middle of next week, where I'll focus completely on how you can prep for the exam. And also I'll just try to do like a high level recap of all the topics that we have done in the course, so that if you just attend the session, it'll be, or if you watch the recording, it'll kind of be a bit of a quick crash course kind of a recap. Okay, I'm not saying just doing that will be enough, but hopefully it'll be useful in terms of just highlighting the key points of the course. Okay, but beyond that, very quickly, what I can say is that the paper is in two sections, both of which have equal weightage. And in one section, the questions are very similar to the assignment problems that you have seen so far. In fact, some of them are, I would say some of them are, if not identical, they're very similar with, different numbers and so on. So, if you just go through the assignment problems and, make sure that those make sense, then I think, then I think it'll be a decent amount of preparation already. And, as I said, many of them are fairly straightforward questions. There aren't really a lot of knowledge-based questions, I would say, in terms of, I mean, to some extent, it's good to know the running times of the popular algorithms and things like that, but there's nothing too crazy in there. So essentially, if you just revise the material, the basic algorithms, I think you will be good for the first part. And as I said, the format is very similar to the questions you've already seen in the assignments. Okay, so make sure to revise all the assignment problems once. Don't learn them by heart or anything, but just go through them and revise them once. Okay. Now, the second part, the way it works is that I don't remember exactly how many questions there are, but I think there are probably like 3 problems where you'll have to read a problem statement. It's like a problem statement that comes up in programming contests. Okay, so there is a story. The story may be a bit long, so you have to patiently read it. But for every such problem that you read, there will be multiple small questions. Okay, and some of them will just ask you to work out some sample tests, some sample examples. Some of them will ask you to think about approaches to the problem. So we have seen some, I don't know if you remember the assignment problems, like if you remember the problems with the dragons and so on. So it's kind of like that, right? You go through a Spider-Man where I don't remember which week that was, but yeah, I mean, there are these questions where you read up on a problem statement and then you solve multiple small problems about that problem that you have read. Okay, so it's not just directly jumping to the answer. It's more about work it out on some special cases and what looks like a likely approach. Will a greedy algorithm work or not? So you just have to think on your feet. So so I think the knowledge of any specific previous problem may not be very helpful here. It's really more about being able to assimilate a problem and be able to think through it. So the experience for the second part will probably be very similar to the experience that you have when you're doing a programming contest. At least that was our intention. Because of various logistical limitations, we are not able to do a programming based exam. So through these MCQs itself, we are trying to kind of break it down to a point where the questions that you would typically ask yourself while solving a contest problem on pen and paper, right? Before you write the code, you will work out some small examples, you will go through some approaches. So these questions will kind of simulate that thought process. Okay, so so the best way to prepare for this, I think, is to, generally speaking, participate in contests where you go through this process multiple times. Having, generally speaking, I think practice would help. Okay, so I hope that helps. As I said, in terms of material, we'll be covering all techniques, including we started off with ad hoc, so there will be some like puzzles, which don't involve any specific algorithms. Then we have greedy, and I think we have disjoint set union, searching and sorting. And then we have all these graph algorithms where I think we started off with BFS, DFS, spanning trees, shortest paths and flows. And finally, we have dynamic programming. Okay, so hey Raviraj, that's a great suggestion. In fact, that is a video that I'm actually working on this weekend. The thing is that there are so many resources and many of them are so great. Yeah, I'm myself a little bit overwhelmed by how much good material is out there. At the same time, I don't want to point you to things that, I've not tried at least a little bit myself. So that's kind of why it's taking a little bit of time. So I think, hopefully it will be ready by tomorrow. In fact, I'm also quite excited about the remaining DP videos. So I know we've been very late in pushing them out. I think you don't really need them for solving the assignments of the exams, but I think the practice will be helpful. So if you have the time, hopefully the DP videos, the remaining videos will be live by tomorrow. So if you have a chance, please go through them, as you work through the assignment in the exam. Okay. Fine. So, Sunny, you're saying that your concepts are good, but in implementations, you faced a lot of problems. Right. So, at least for the NPTEL exam, you don't have to worry too much about implementations. Okay. So, if you're asking in the context of the exam, there is no coding at all. And if your concepts are good, then that is all that you will need. But implementations will be important if you want to do well in CP, or if I don't know what kind of like goals you have, whether you just want to do CP for fun and become good at it, or if you're planning to do some sort of a job that involves writing a lot of code and things like that. If any of these things are true, then there is definitely a need to also be, comfortable with implementations, right? So if it is any consolation, one thing I will say is that everybody faces problems with implementations. Okay, if you look at professional developers, even ones who are very experienced, can be very frustrated by their coding related tasks. Okay, so I mean, of course, with experience, there are many things that you become like quicker at identifying. You will have a sense of patterns, and you know what and all to look out for. But still, I don't think it ever gets peaceful. Okay, so I think this sort of thing is like a permanent adventure. But yeah, it can be a little more frustrating in the initial part, I would say. You really have to sort of keep at it, and try not to be frustrated with one thing for too long. So if you are really stuck on, I mean, I know that it can be like really annoying, especially when you are in a situation where you've written some code and you're very sure that it's correct, but it's still giving you some sort of an error, or you're getting a TLE or a wrong answer, whatever. Then it's very hard to kind of get it out of your head, and you really want to uh, fix it before you go to sleep or whatever. So it can be weirdly addictive, and then it can also be a little frustrating. I would say try to discipline yourself a bit, where you really take the time off and come back to things with like after you have maybe gotten a break, gotten some rest, or just thought about other things, or switch to a different set of problems before you come back to this. Because sometimes a fresh set of eyes, like your own eyes, but after some time, can be better at catching bugs and problems. So of course, this advice will not apply within a context, although it still might, in the sense that you might want to switch to a different problem and come back to the one that you're stuck on a little bit later. And I would say try to see if you can find a partner or a study group that you can be a part of, because it really helps to not do it alone, like to have some friends with whom you can exchange notes and clear your doubts, and some friends who will actually help you with your code. So you have to be real friends to be willing to look at your code and help you debug it. And try to return the favor also. I mean, I think it's a great exercise to help other people debug their codes also, because it helps you develop that skill as well. So yeah, I think those are yeah, so those are, I think, a couple of things that come to my mind. Um, I think the plan is to keep the Discord group for the course. We don't plan to close it down, we'll just keep it, even though the course is almost getting over. And, I would encourage you to use the group to find people that you can work with and, hopefully improve your skills as you go along. By the way, I just noticed that Ramesh Bakshi had asked in the chat on YouTube um, if I can give some tips for preparing for the exam, the NPTEL exam. So fortunately, I think Sunny here had asked almost the exact same question. So I think I've kind of addressed that as we went along. So I hope that that's fine. But let me know if there's anything specific that you wanted to know that I haven't covered. Okay. So yeah, Sunny, I hope that that helped. Okay. And right. So do let me know if there's anything else that that you'd like to know. Okay, great. Thanks. Yeah, a very good day and evening to you as well. All right. So I think we do have like a little bit of time before before we get to 8 p.m. So let me see if I can use that time to talk a little bit about the TP assignment. So I think one of the questions that's there in the week 12 assignment, which is kind of like a programming assignment because I think the numbers are large and you'll need to write some code to solve it. So, so I think the question was the following. You want to distribute K toys in n boxes, and each box, so let's say there are 3 boxes, so each box has a limit. So the number of toys you can put into box 1 is between 0 and A1. The number of toys you can put in box number 2 is between 0 and A2. Between 0 and A3. Okay. So, so you're given some constraints in this form, and you want to know in how many ways can you distribute K toys in N boxes given these constraints, right? And you want to make sure that each of these K toys goes to exactly 1 box. So no toy is shared between 2 boxes, and no toy is left out also. Everybody gets a home, they get a box to go to. So in particular, for example, if you have like 100 toys, but all of these boxes have limits which are like maybe 2, 5, 7, then what can you say? In how many ways can you distribute 100 toys in 3 boxes with these limits? Anybody? Yes, exactly, 0, because the boxes are too small, and it's simply not possible to do this, right? And okay, so that's just more of a sanity check. Make sure that we understand this correctly. Let's say you have something that looks more like a partition, 50, 25, 25. Then what would the answer be? Sort of predictable, I hope. So the reason I'm okay, right, 100 C50 into 50 C25. Okay, let's think about when do we consider 2 ways of distributing toys in boxes to actually be different. Okay, so let me just recall this from the problem statement. So 2 ways are different if some box has different number of toys. In fact, let me try to read it out from the problem statement. 2 ways are said to be different when there exists a box that has a different number of toys, right? So let's say that So would we agree that if you had to distribute 100 toys and the limits are like this, then you would have to put 50 toys here, 25 toys here, and 25 toys here? There's really no other way to do it, right? I mean, because if you try to put fewer toys in any of these boxes, there would be one toy that would be left out, but the other two boxes are anyways already full, right? So for example, suppose you try to put 49 toys here, right? Then you would be left with 51 toys to distribute, but these two boxes only have a limit of 25 and 25. So you would not be able to distribute them at all. So there's no distribution which, puts 49 toys or less than 50 toys in the first box. For the same reason, there's no distribution which will put less than 25 toys in the second box or less than 25 toys in the third box. Yeah, is that fair? And is that reasonable? Okay, great. So given this, would there be two different ways of doing it? Once again, two ways are different if there is a box that has a different number of toys. So in particular, the toys don't have any identity. They're indistinguishable. So even if it's a different set of, so I think the answer that you have given, Sudhanshu, would be correct if the toys were distinct, right? So like then, yes, then you have to give some importance to which 50 toys went into the first box. But right now, you only care about the number. So it doesn't make a difference, right? So it's just one. In this case, it's just one. Right. Okay, good. So, right. So I think there are some examples that are given in the problem statement. I think the first three of them are like small examples, which are just like the ones we discussed. And the fourth one is an example that you can use to sanity check your answer. So if you're writing a program to figure this out, make sure that you take your answer modulo 10 raised to 9 plus 7. Otherwise, your final answers may not tally. So there's one example there that helps you sanity check that you have the right approach. So so sort of the hint that I want you to think about here is, what are the partial solutions that you want to compute? So one way to think about this is to say that you want to think about let's say the number of ways of distributing J toys among the first I boxes. So here I ranges from 1 to n, which is the number of boxes, and j ranges from, I guess for the base case, you could even take this as 0. I don't think it matters so much. 0 toys, 0 boxes. There's really nothing to do. So I guess you could think of it as, having at least one box and one toy to work with. Yeah, I don't think the edge cases are of course important, but I think you can start from one, should be fine. You should still be able to compute the base cases quite easily. So, so these are kind of the partial subproblems that I think are worth looking at. And essentially, what you want to figure out is, first of all, which is the subproblem that corresponds to your answer. I think that's reasonably clear. I won't say it explicitly, but there are some natural values of I and j that you can plug in, which will give you your final answer. And therefore, what you want to do is figure out a way of solving this recurrence. So d of I comma j or dp of I j would, essentially think about what are you going to do with the last box? How many toys do you want to put in the last box? Something along those lines will help you break this up and come up with a recurrence. So think about that. The other thing I wanted to clarify was, I think the word pseudo polynomial comes up in the first, in the week 10 assignment. And Okay, so I think if you, if you haven't heard of this term before, I think I would imagine that if you've seen classic DP algorithms like for knapsack and so on, you would already be familiar with what this means. And that was sort of the expectation. But just to be sure, let me say that, if you have a DP where you're working with, let's say, some numbers or weights, you could be working with some n objects, but let's say you're working with a maximum weight of, just say capital T or something like this. So let's say that, you end up computing something for every number T, right? But your input is just N, okay? And T could be something, T could be a number that is really, really large. And it's basically just some weight or something that's been given to you. But your input does not really have T different things. It just has this number T. That's the input, okay? So the amount of space you need to write down this input, this number T, is really just log T bits. Okay. You don't need anything more than that to write down the input, which is the number T. Okay. So if you have a DP table which has, T rows or T columns, or you have a recurrence that is going to evaluate T many entries, then, what is the running time of T? What does it really mean? You can think of T as being 2 raised to log 2 to the base T, right? This is T, right? I mean, the log and the exponentiation and the log cancel out, right? So T can be thought of as 2 to the log T. But 2 to the log T is the size of input. When you're just given T as a number, if that's the input, then, the size of the input is just log T. So your algorithm, which is taking, some T time or T squared time or some poly in T time, it's actually exponential in the size of the input. Okay. So such running times are called pseudo polynomial because, well, if T happens to be bounded as some polynomial in N, then it's okay. Then this algorithm will be, well, just because T is bounded, any polynomial function of T will still be a polynomial of a polynomial in N. And so then that's polynomial in N. But if you're not promised anything like this about T, and T can be some arbitrarily large number independent of N, then this running time is not really polynomial. And that is why it's called pseudo polynomial. Okay, so that is something that, I just wanted to share this definition with you so that it makes sense. We've actually seen this come up once in the course, if you remember, when we were doing weighted shortest paths, and I said you have an edge UV whose weight is, some number, let's say T. And we said that, okay, we can use, if all the weights are positive integers, then we can still use BFS. And we can use BFS by creating T many intermediate nodes, right? T intermediate nodes. And run BFS. And remember at that point we said it's very, very expensive because the number of nodes that we are creating is proportional to the weight. And the weight may have nothing to do with the number of vertices and edges of the graph. You may have a graph with like a, 1,000 vertices and, maybe a few thousand edges. And the weight could be something that is, a trillion or something, right? Now, to even write down a trillion, you need a very small number of bits. So the size, like the amount of memory you need to represent these weights is very small. But if you want to create as many vertices as the weight of an edge, then though you are doomed, right? Because you are creating, you're really making a mess. Okay, so hopefully, that conveys the idea of what it means for something to be pseudo polynomial. You may be given that your weights are between, your weights are 1 or 2. In that case, it's not a problem because your weights are constant, small constants, right? And sometimes you may be told that every edge has a weight which is some number between 1 and n, then also this is fine, because, well, I mean, you still have to check if, it is okay to do running time proportional. Like, you'll have to do the usual thing of checking the constraints for a CP problem, but at least theoretically, the running time would still be polynomial because the weights are bounded by a function of n, or they're bounded by m. But when the weights are unbounded, this could really be a problem. And this is something you have to be careful about. So hopefully this helps you address some of the questions that have this pseudo polynomial option. So go back and see how many DP entries you might actually be computing. Okay, so fine. I think that's kind of all that I wanted to say about the DP related assignments. If you guys have any doubts, then let me know. I know that in Discord, I think there were some questions about the max flow solutions. I think we are kind of out of time right now. So what I'll do is I'll try to post either the sample solutions or an explanation in Discord itself. Okay, so that's what I'll do. But for now, unless there are any more questions, I think we can wind up this session and kind of call it a day and wrap this up here. I know that, yeah, you probably have exams coming up next week, and I'd like to wish you all the best. But this is not goodbye, because I'd like to do one more final live session where we can have a chat about, how the exam's going to work, and just recap all the material once, like a bit of a crash course revision. Hopefully that will help. Okay. So, all right, I guess I don't see any more questions either on YouTube or in the Zoom chat. So I'd like to thank all of you for joining on a Saturday evening, and see you soon. And good luck, all the very best from all of us. Thanks, Sudhanshu, Raviraj, and Sunny. Appreciate you joining us. And bye for now. So I think we can close the live stream as well. Hello. Right, I just wanted to confirm if the live stream has been stopped. Okay, so I'd just like to say that at this point the meeting is done. So what I'll do is I'll exit the meeting so that hopefully that will automatically cut off the live stream. Yeah, so thank you so much.